So this video will cover a few examples with the Pythagorean theorem. By now, you've probably heard of the Pythagorean theorem in your studies of mathematics. In 300 BCE, the mathematician Euclid wrote a 13-volume work on the subject that is included with this famous theorem. In this collection of geometric axioms and postulates, it lays the foundation for 2- and 3-dimensional geometry, the Pythagorean theorem. In right-angled triangles, the square on the side opposite the right angle equals the sum of the squares of the sides containing the right angle. Euclid's Elements, Book 1, Proposition 47, written in 300 BCE. However, perhaps this important historic work was a collection of the times. Predating this encyclopedia of knowledge was a Babylonian clay tablet, Plimpton 322. Well, as an introduction to this idea, what I've done is on this first slide is shared 4 different right triangles. You can see the 90-degree corner in the lower right of each picture. And what makes these special Pythagorean triangles is that each of the side lengths are whole numbers. So for example, the first triangle are actually the natural numbers 3, 4, 5, and you can see mathematically 3 squared plus 4 squared equals the diagonal side squared, and 9 plus 16 equals 25. The second triangle is the 5, 12, 13 triangle, showing the short side 5 squared is 25 plus 12 squared, 144, is exactly equal to 169 units. And the same is also true for the 7, 24, 25 triangle and the 8, 15, 17 triangle. In this next slide, you can see this symbol here on the left. Notice that this is the symbol of the Pythagorean school and also represents the squares of a right triangle, showing that the area of the base leg squared equals the square of the hypotenuse, which is a side opposite the right angle. So as you can see with the units marked off in equally spaced squares, those 9 units plus 16 units is exactly equal to the 5 by 5 square that is along the diagonal side. To further explore this idea, what I did was I drew a series of gray squares here, and then I chose different lengths for the sides of the square. So for my first 2 squares there, I chose a side length of 5, and for those 3 squares in a row, I chose the side length of 7, and then for those 2 squares connected, I chose a side length of 8. Well, since the side length is 5 for the triangle in the first row, the base is 10. And if we use the Pythagorean theorem, 5 squared plus 10 squared equals the square root of 150. Well, that's not a perfect square. And the best we can do is simplify that to 5 square root 6s, but it's not a natural number. Similarly, if the side length is 7 and the base is 21, the hypotenuse is the square root of 490, which again is not a perfect square, although we can simplify it to 7 the square root of 10. And for the third example, the 8 by 16, we can see that the hypotenuse is the square root of 320, which again is not a perfect square, but that's equivalent to 8 square roots of 5. Going back to the first row, if instead we have a height of 5, but we make the base 2 units longer so that it's 12, then we do have a Pythagorean triple. So although it's close to the shape of 2 squares next to each other, we needed a little bit more distance along the base, and then the hypotenuse is 13 units. Similarly, for the 721 triangle, if we extend that base to 24 by adding 3 more units, and we put them in place on the base, then the hypotenuse will be exactly 25 units. And lastly, the 2 squares on the bottom, 8, 16, well, if we shortened the base by 1 unit instead of 16. If it was 1 less and was 15, then we would have the 8, 15, 17 triangle. But if you think in practical terms, if you're using constructions and you want triangles that are very close to 2 or 3 squares in a row in the ratios, like a 1-to-2 ratio or a 1-to-3 ratio, here's an example of 3 Pythagorean triples where all of your unit measurements will be rational. In fact, here they'll be the natural numbers because they're Pythagorean triples. Next, we return to this slide of the 4 starting Pythagorean triples. These 4 primitives are very important because they're the most common ones on the SAT. So as you get ready for the SAT, make sure that you know by heart these 4 triangles in your study: the 3, 4, 5 right triangle, 5, 12, 13, 7, 24, 25, and 8, 15, 17. This is because at least 80% of the problems that you see in these geometric designs are in somehow using these ratios in the design itself. So you can save a lot of test time if you recognize, oh yeah, there's a 3, 4, 5 triangle there, or a 5, 12, 13 triangle placed there in the composition, or 7, 24, 25, or 8, 15, 17. Further exploring this idea of the right corner triangle, you could say which numbers you could also check using the Pythagorean theorem whether a triangle has a right angle at corner B. For the first triangle, which is a 5, 10, 13 triangle, we can see that, if you give me just a moment here, this side is 5, the base is 10, and the hypotenuse is 13. However, this is not a right triangle. If we add them together, 125 units is certainly not equal to 13 squared or 169. In fact, you can see that we have an angle greater than 90 degrees. It's an obtuse angle. Similarly, for this triangle, the 5, 12, 10 triangle, although it does close a triangle space, the angle in the corner is not a right angle. In fact, because the hypotenuse is not 13 by 10, it's shorter, we need an acute angle. That side is actually like leaning forward so that we can close the triangle. So here's the idea of the 5 side as an upright 90 degrees. Here's this same 5 side upright, but then it wouldn't attach to the hypotenuse of 10. However, here we have a perfect right angle because 5 squared plus 12 squared equals 13 squared. So you can use the Pythagorean theorem to check if an angle is a 90-degree angle. You'll further explore this if you continue with mathematics in Algebra 2 with the law of cosines. Here's a picture of a very old clay tablet. This clay tablet is from the Babylonian Empire, 300 years before the Common Era, and has a list of Pythagorean triples in their sexagesimal base 60 number system. The cuneiform wedge marks show a list that includes the triangle 3, 4, 5, 15 times larger. It's listed in those cuneiform marks as 45, 60, 75. Also present is a 65, 72, 97 right triangle, and other ones with integer values with decreasing slope ratios for each row representation. Was it for architectural use? Well, this list, which was a clay tablet possibly for a worker or student or architectural apprentice, had a list of different shaped triangles. Remember, we're talking about the ratios of the sides, but all of the measurements in these constructions would include the diagonal side also being a natural number. Next, we're going to explore some modern uses of the Pythagorean theorem. I've chosen 4 examples that I've written. The first one is for land distance or ground distance. The second is for vertical distance along the wall of building. The third is an application to a robot that can move in 4 directions. And the fourth is a 3D problem, also called the double Pythagoras problems. These 4 problems are in increasing levels of difficulty. For example 1, to save time, Mary walks across the diagonal of a 40 by 75 rectangular field. How much shorter is her walk across the field than if she walked along the perimeter? Well, her normal walk around the rectangle field would be 75 meters plus 40 meters to get around the field, which is a total of 115 meters. But since she's going to walk across the field along the long diagonal from corner to corner, we can use the Pythagorean theorem. D squared equals 75 squared plus 40 squared. So D squared equals 5625 plus 1600 is 7,225. Taking the square root, the distance across the diagonal is 85 meters. So when Mary walks across the field, the difference between her normal route and her diagonal shortcut is saving 30 meters of travel distance. The correct answer is 30 meters. For the second example, an 18-foot ladder is leaning against a brick wall. The foot of the ladder is 6 feet from the base of the wall. If the ladder is moved 3 feet closer to the wall, how much higher will the top of the ladder touching the wall reach, round to the nearest tenth of a foot? Well, for this example, I drew the building itself as this colorful mosaic of dots. But the black ladder, that's the ladder leaning against the building. We have a side view here. The ladder is 18 feet, but it's chosen by the person who anchors the ladder, the base distance away from the building. This might be an easier climb for, say, a fireman or service worker because it's less steep. But we can see how high the ladder reaches. For the first example, if the ladder is 6 feet away from the building, we have the right triangle formed from the side. 6 squared plus h squared is 18 squared, meaning 36 plus h squared is 324. Subtract 36 and take the square root, and the height is 16.97 feet. For the second ladder, we have 3 squared plus h squared equals 18 squared. 3 squared is 9. Subtract 9 from both sides and take the square root, and we get a height of 17.75 feet. Well, the difference between those two heights, 17.75 minus 16.97 is 0.78 feet, rounded to the nearest tenth. That's 8/10 of a foot. So believe it or not, even if we extend the ladder out 6 more feet, which might be a safer climb for a worker, we're still it's just about a foot less in terms of the total distance, the rise up the height of the building. The correct answer was C. For the next example, Seymour programs his robot Kame to move with a computer program. He instructs Kame to move in the following directions. For command 1, move 1 unit north. Step 2, the robot turtle will move 7 units west. Step 3, 3 units north. Step 4, 4 units east. Step 5, 9 units south. And step 6, 5 units west. The final displacement of the turtle is 9 units west and 5 units south. The goal here is to figure out if we were to command the robot turtle to go directly back to where it started, what's the total distance between the starting location and the location when the turtle walked through all 6 of those commands. Using a compass rose, we have north, south, east, and west. What we can do is we can split the orders for the robot into east and west commands and north and south. So for example, in blue, the robot went 7 units west, then 3 units east, then 5 units west. So its final displacement was 9 units to the west. In terms of its north-south commands, went 1 unit north, then 3 more units north, and then 9 units south, for a total displacement of 5 units to the south. I took the liberty of using the coordinate plane so that east would be positive values and west would be negative values. Similarly, north would be positive numbers, and south would be negative, so that I could keep track of the final displacement of the turtle. With that nice quick sketch, you can see as well that if the blue dot is where the turtle began, that it's certainly to the southwest of its starting location. But now we can set up a right triangle. We make a right triangle with the legs 9 and 5 units, and 9 squared plus 5 squared is d squared, which means 106 is d squared, and the square root of that is approximately 10.3. Therefore, the robot turtle is 10.3 units away from home. The last example is a 3-dimensional example where we use the Pythagorean theorem. This question is from the class worksheet, and it's number 20, and says, a cube of side length 5 is shown at the right. What is the distance between the center base of the cube and the midpoint of the vertical edge as shown? Well, I explained to class, what if I had a work box that you have to put your papers in, like say when you're done with a quiz or a homework or an exam? And that's the open box. Well, after students submit their work, then let's say to a student, hey, can you pick up that box and bring it over to the teacher's desk so I can grade it? So if you put one hand on the bottom of the box and then one hand on the side, we're talking about the distance between those two locations. One hand being down at the base of the box and the other supporting it on the midpoint of the vertical edge. So we want to say the distance between two hands cradling or supporting the box. Well, the first thing we have to do is we have to figure out the distance of that star in the base of the box, as we want to find the diagonal distance to that corner. So since that's at the midpoint and the star is at the center, we have a bird's eye view here, and that means that the legs of the right triangle are both 2.5, or 5 over 2. So 5 halves squared plus 5 halves squared is equal to 25 quarters plus 25 quarters, or 50 quarters is the diagonal squared. Taking the square root, we have the square root of 50 over 4. I'm going to leave it in radical form because we're not done with our math. For the next step, we're going to now construct the triangle that contains the distance we're trying to find. So now that we have the base distance from the center of the box to the corner, we also have the upright distance is halfway along a side length of 5. So that means that, here I'll use the laser pointer. That means that we just calculated this base distance from the center to the corner is the square root of 50 over 4. And this is half of 5 units because it's a cube of 5 units. So this distance is a half of 5, or 2.5. So now we can do the vertical Pythagorean triangle, which is 5 halves squared plus 50 over 4, the square root of 50 over 4 squared, which will give us the distance we wanted to find, like the distance between two hands holding the picked up box. Then we'll have 25 over 4 plus 50 over 4 is d squared, which is 75 quarters, taking the square root. I rewrote 75 as 25 times 3. So we get 5 square root 3 over 4 over 2 is d, and the correct answer is B. 5 root 3 over 2. All right, I hope this video was useful to you as you prepare for the Pythagorean theorem on the SAT. Thank you for watching my video.